All right. So in the next section, we're going to talk a little bit about research that's inspired by practice. So it's actually a really great segue. And we have two researchers who are going to talk a little bit more from a systems perspective. And as we switch this up, should we give people a break? It looks like people really need a break. Okay, 3 minutes if you need more coffee. Okay. So the next two talks, which are our last perspectives panel, are talking about research inspired by practice. And we have two wonderful speakers. Don't worry, I know the coffee wasn't fully refreshed. We'll give you a little bit of time after the speakers before the breakouts to refill your glasses. So let me introduce Laura Freeman to introduce herself.
Thanks, Zoe. Good morning, everyone. Laura Freeman. I am a faculty member with the statistics department at Virginia Tech, so not a systems engineer. But before I was a statistician, I was an aerospace engineer. So I feel like I've just kind of circled around systems thinking. Am I not loud enough? Okay, sorry. Maybe I'll just hold it. So I work at Virginia Tech as the deputy director of our National Security Institute. And just a little background on me to kind of tie into this session. When I finished my PhD back in 2010, debating different career pathways between academia and industry, and I actually ended up at the Institute for Defense Analyses. One of the reasons I ended up at IDA was because I wasn't quite sure what an academic research trajectory looked like for me. And so I think that gets to kind of the heart of this session. And then I went over to the Institute for Defense Analyses and spent 10 years testing every type of system imaginable, things from business management systems, electronic health records, the F-35, all these different types of systems. And that gave me this perspective of how these systems are all very different. Electronic health records, nothing like a fighter aircraft. But that there was a lot of systematic gaps in how we address the understanding of our current system capabilities. And so now I'm primarily focused on enabling the adoption of AI into critical workflows in a national security context, but really just across the federal government and the concerns that they have there. And all that to say that has driven me to an infinite list of research questions. And so I think there is a lot for academia to do to engage as we think about how AI comes into our workflows, into our teaching and education. And so I'm going to give you a sample of that today. So to kind of set up my talk, I'm going to be focused mostly on test and evaluation, but wanted to tie it into the larger acquisition process. So forgive me, this is a bit of an eye chart. We're really good at those in DoD world. And I stole it from the director of test and evaluation, Chris Collins, developmental test and evaluation, Chris Collins, and a talk that he was giving on how we need to think more about an acquisition life cycle continuum. And so the point of this slide is really to think about the systems engineering V and how that is collapsing. He would call it collapsing to the systems engineering I. And this is at the heart of kind of waterfall versus agile acquisition and what the type of information we need there. And so depending on how you feel about the systems engineering V and how software is changing the nature of our systems, and now artificial intelligence is changing the nature of our systems, I think there's a much tighter coupling at every level of our system design with the validation and verification of that design. And so I'm really going to focus on the right-hand side of the systems engineering V today, but at every step along the way, there are things we need to be thinking about in terms of how we design our systems so that they are designed for testability so that we can get assurance of the system going forward. And before I got started, there was a quote from Sanjay in the previous session talking about humans and how we've trained people to be machines, where he said, what do you do with products? Well, you test them. So I immediately lit up. I'm like, oh yes, we do test products. But then the follow-on was, if the product is too creative, that's a problem. And I think that is actually the heart of what I want to talk about. Not that the F-35 is creative, or anything like that. But what we are seeing with software-enabled capabilities, with AI-enabled capabilities, is the ability for products, our systems, to change rapidly and also to have these emergent and unexpected behaviors. So creative might not be the right word, but what we need to do to think about how to test, evaluate, and assure those systems now that they can change really rapidly. So there's really kind of two lists that I'm going to go through, and I'm going to go through them pretty quick here to leave time for questions. But on one hand is, what do we need to do to test and evaluate our AI-enabled systems? What do we need to think about differently? And on the other hand is, now that we have AI capabilities, how do we re-engineer our test and evaluation processes leveraging that AI? So my background, detailed background, experimental design. So I'm going to go through this just like an experimental design person would go through. It's like, what are you trying to measure? What are the factors that are going to impact it? How do you vary those for efficient testing? And then thinking about that across the acquisition lifecycle. So first of all, this was kind of at the end of our last session, but how we think about human AI interactions and human machine teaming in this new paradigm. So to be able to responsibly deploy AI, humans need to exercise appropriate judgment when deciding to use them, and that needs to be done in the development, deployment, and use of these AI capabilities. And so I think there's a real gap there in terms of how we assess the human-machine team. And lots of people are doing research in this space, but kind of the points I want to make for adoption at scale are, we need measures and metrics that are reproducible. We need validated scales that are meaningful to humans so they can interpret them and say, yes, this is a trustworthy system. And so two of the key kind of things that I'm highlighting here is that that's going to come from both scales, survey questionnaires, measurement, as well as more quantitative measurements of things like reliance. And what we want to avoid, which also came up earlier, is we really want to be on that green line where the capability and our use of that capability are matched. We're not over leveraging a capability that's not ready to be used, and we're not underusing a capability that's far more advanced. And so getting to how we can capture this quantitatively and then experiment around this is a really important place where we need more research, more methods, test beds, to reflect on a conversation Zoe and I were having last night, that capture that human-machine team together in building out that capability. Another area that I think is underrepresented in the research is thinking about the coverage of our data. When we talk about AI, we're talking about algorithms that learn from data. And so having ways that we can define the robustness of the data, the coverage of our data, typical use cases, where I like to refer to it as the operating envelope. That's coming from like the aerospace background there, where we know where planes are certified to operate, right? They have their nice little envelope. We need that for AI, and that has to be in terms of factors that are definable. And so this is another area of research that we've been focusing in a lot, but thinking about what coverage means. Because once we understand coverage of where that model was trained, then we have an understanding of that performance envelope, and we can minimize unintended biases and understand failure modes that might be coming down the road for us. So there's a big challenge with coverage in that we have to actually learn for these learning systems what factors matter to them. And so kind of the next piece that I think is critical as we move forward in testing and evaluating AI is developing processes where we are iteratively learning about what features matter. And so just over here on the left, I have a little kitschy example that we were doing. This is the planes data set, where it's got planes in Northern California and Southern California. And we noticed as we were going through it with a computer vision model, YOLO, when we were training in the South and then testing in the North, we were seeing a performance drop. Data quantity was not the issue, right? So in Southern California, we had 22,000 images. In Northern California, we had 10,000. So there was much more data in Southern California. But we didn't see this drop when we went the other way around. So it took us too long to figure out at the end of the day that when you looked at coverage of the color contrast, RGB, hue, saturation, and illuminance, which gets to things like contrast. In the north, that there was a much more diverse coverage across all of those than there was in the south. So we were seeing more variability in our contrast, essentially, in the north, which sounds obvious now, but in 2020 it was not obvious to us as to why this was going on. And that was a learning process that we had to go through with detailed experimentation. And so that detailed experimentation really needs to span not just the model, but also the system and the system integrated with the human operating in the context that it's going to be operating in the real world. So Jitesh and I actually worked on this paper also in 2020. COVID years were fun. Where we talked about, what do we need to do for testing of the training data, the model, the system, and the system of systems. And had the opportunity to actually then go implement this concept in a federal government program where we were looking at computer vision to support Intel analysts. So I don't know if you guys know what Intel analysts do all day. They stare at a screen. It's got to be a very difficult job. But just like anyone monitoring in airports and other things, you're staring at a screen and you're looking for anomalies, things that raise a red flag for you. And so in this application, we had spent 3 years actually really focused on model T&E. There are all sorts of industry vendors providing all sorts of models with, they were really kind of achieving peak performance. And then our team got the opportunity to come in and say, okay, well, let's go put it in use. Let's go put it in the system. And so we plugged it into 2 different systems. One was an on-prem deployment and one was a cloud deployment. Immediately learned that even though our models were doing great, the inferencing timelines just did not work in a cloud deployment. And so that drove a complete re-engineering of what was acceptable from the model. So we should have done that, maybe on day 1, not on year 3, when we got those first performant models. And then we put it in operational context where we were looking at really long clips where, an Intel analyst's attention is really going to suffer. And started to ask them about how this was working and where it worked and where it didn't. And the result of that was that we found all sorts of new failure modes. In these long clips, you might have things like zooming in and out or panning across the model, but the model was trained on much shorter clips. And so we quickly learned that the model failed in situations where you really wouldn't want it to fail when you put it in this operational context. So again, that should have been day 2, not year 3. And then the human piece of this, we learned that often the model could be distracting to an analyst who was looking for very specific cues, the way that they were trained. And so it wasn't necessarily helping them in all sorts of scenarios. But additionally, it didn't really save them any cognitive burden or any time because the process of staring at the screen is what they spend most of their time on. But then when they see something, they have to go put it over in an Excel spreadsheet and log it and then generate a PowerPoint deck because that's what leaders are used to seeing. I hate PowerPoint, but everyone uses PowerPoint. And all of that process was what takes them away from actually monitoring the screen. So we engineered the solution around the wrong workflow. So all of that to say that we should start using these capabilities early and often, and we should put them in the most operationally representative environments that we possibly can so we can have that learning on what we need to test as quickly as possible. So I'm going to skip that for the sake of time because I already kind of covered it on the last one. But also that experimental design, just highlighting that experimental design is a really critical component of how we learn about these models. And so this is a little bit of an eye chart to say that we have a really rigorous methodology, I swear, behind this, where we partition training data and test data, and we did all possible combinations and retrain models. And we're able to show that you can learn through this systematic process what factors matter to a model or not. And so a lot of people will talk about the complexity of being able to test AI, and they'll use terms like combinatorial explosion. And so this is really getting at the fact that, yes, these are complex algorithms resulting in complex models, but we can learn what those the biggest drivers of model performance are. And we should, because then we know where it will work and where it won't work. So just to kind of highlight something here, so like biome is what this one says, no, yes. So when all the biomes were included in the training data set, our performance was way higher than they weren't. But over here, like the season didn't have a huge impact. And so that gives us a feeling for, okay, if I change a biome, if I go to a new part of the world, I probably need to think about retraining my model. But the seasonal differences were minor. And humans can make decisions, coming back to that responsible use, that we need humans to have judgment on when they should and should not be using these models. Having these types of explanatory charts can help with human decision making. So I'll kind of highlight that coming back to the acquisition life cycle, this can't be a one and done activity. We need to be thinking about it through our collapsing systems engineering V. Or this is also work we did with Jitesh, which, just side note, this is so Virginia Tech, Purdue. So like Virginia Tech and Purdue. We called it the VTP model. Anyway, that we need to be thinking about how we're going to test and evaluate these systems throughout the acquisition lifecycle. So that is when we are designing and unit testing and integration testing and acceptance testing, but also once it's fielded. And that comes back to kind of acquisition at large and thinking about how we engineer these systems. Because it's very expensive for me if I've got a deployed health records management system in the field to be running a test, sending an analyst out saying, let's go put some test data in. But if I've engineered that system to be testable and I have metrics coming out and I've learned what factors matter to that system, and then I've maybe instrumented those input variables as well as my output variables, now I'm in a monitoring state. And I can automate those processes and have things like drift detection and the ability to predict unintended consequence and or deactivate or disengage the system. So these kind of concepts that we want to test for need to be baked in our systems design process. So I think this is my plug to you all. If you are interested in test and evaluation, there's a whole realm of opportunity in this space to help drive us all forward in our responsible use of AI. And there's, I think, a big opportunity for academia to really defining new methods. Everything from test adequacy to all the properties that we want to achieve with responsible, reliable AI, robustness, security, safety, and assurance. At large. And so I think this is an interesting space for people that think about systems and engineering systems to be engaged, because it's not just engineering the system, it's how do you verify and validate on the back end or test that it does actually do what it was intended to do, especially when what it's intended to do might be to learn over time. So just real quickly, because I'm trying to end right now, I'll hit artificial intelligence impact on T&E from the other perspective. And I think, actually, I'm just going to talk through this slide real quick. But there's, on the flip side, our test processes today are also the same test processes that we've really used for decades. At this point. And so there's an opportunity to think about how do we get the information that we need to decision makers faster and more efficiently. And so just a few things that we've been playing with, automating and accelerating test design. You cannot ask ChatGPT to build you a design of experiment, but you can ask it to help you explore factors and then write code in R to generate de-optimal designs. And those do work. So. So a test case generation, actually scripting out what you need for the tests, generative AI has been very helpful with. Operationally realistic, this is kind of the whole NVIDIA omniverse, thinking about how we can build scenarios and environments coming back to that we need those environments with humans to be able to test systems. How do we push forward in that space? And then also using AI for the continuous monitoring of the AI. So I'm going to get off the stage on this slide because I think it's kind of complementary to some of the closing comments of the last talk. But also I've been working a lot recently with some of these, as we call them, frontier AI companies, and how we think about getting those capabilities into federal government service. And just the dollar amounts are staggering. It's just like funny money when you're talking about it. 100 billion with OpenAI and NVIDIA. I don't even know what Series F funding, I should maybe learn more about finance, but just the amount of money these companies are raising is driving economies that are beyond my comprehension. And even to the point where Google is investing, full stack development now includes build your own nuclear power plant. So it's just a rapidly changing world. And in that context, I've been pondering kind of the role of academia. And so we've talked a little bit about leveraging capabilities in the classroom and research. At the National Security Institute, one of our kind of hallmark programs is experience-based learning for our students, and we do it cross-disciplinary. So every year we have 200 to 300 undergraduate students across all academic disciplines, and we give them what I think are impossible problems, and we pair them with mentors, and they talk through them, and they work through them throughout the year. So very similar to kind of like your engineering capstone, except it's cross-disciplinary. We're pairing them with industry mentors and partners. And I've found that to be very impactful, and I think project-based learning, experiential learning is something we should be emphasizing a lot more now that we know AI is here. And it's not going anywhere, so the whole conversation about should we tell students not to use it is just insane, because they're gonna use it anyway. I think, though, fundamental research is still key. We were talking about this last night. In academia, we don't necessarily build the next fighter jet. We don't build the next submarine, but we understand the fundamentals that are going to make it successful. And so I think there's really still a key fundamental there that we need to understand kind of the underlying mathematical pinnings of these algorithms. And that also is going to help us inform how we test them, because then you can start to, make predictions about how this should behave. And then, as we do, form a hypothesis and test it. Applied research offers many new opportunities for those of you that have sabbaticals coming up. I would highly recommend doing rotational assignments either within the government or with one of these industry partners. It's been very eye-opening to me to see what challenges they're facing and how we translate that into research. I think close partnerships with industry are going to be critical, and I don't think those have been fully baked yet, especially with a lot of these up-and-coming AI companies. And then finally, kind of my favorite topic is third-party evaluation, operational independent evaluation, and test beds to do that are a critical gap area that I think academia can fill part of. So with that, I am going to stop, and I think I have a minute for questions, and then we'll pass it over to Ellie. Yeah.
So kind of tongue-in-cheek a few times, you said we should have figured that out. So how are we doing on being able to figure it out for the next round?
Yeah. So I don't know. How are we doing? That's a big we. So I think the lesson has been learned in like lots of communities, but I don't know how broadly that is, that we need to understand workflows. So the work that I'm doing right now, they're actually starting on day one with mapping your current workflow and then trying to figure out what AI capabilities can plug into those workflows. So I think that's kind of step one that we should be thinking, we, the collective, industry, academia, the government, need to be thinking about how do we re-engineer processes from the ground up? Because almost all of our organizational processes are based in legacy thinking, paper products, and even though we digitize, we still follow the same process, just digitally now. So I think that is a lesson that is maybe emerging. I don't know how widely, though. In terms of thinking about including the human very early and having, operationally relevant workflows, I think there's a long way to go on that one. So that is something I think systems thinking and driving that forward to where the trough of disillusionment that we were going to enter. We've seen that before, right? In automation, things like Chernobyl, where there were indicators. They just were not obvious. There was not a good human-computer interface there where humans could pick those up. Those are lessons I think we really need to be foot stomping right now and saying, hey, we don't want to do that with AI. Let's think about that human-computer interaction, what we display to humans, how we alert the driver in the car when something is coming, vibrating steering wheels or whatever, to make sure that the human has the cues that they need and the feedback loops between the two systems. So I think there's a long way to go there.
So I'm just curious, like if we look at some other industries, especially in computer science, there's a lot of fundamental research done by Google, Amazon, Meta, and so on. Right now, we're not seeing that much happening in engineering audiences and like in your interactions, like in systems engineering and so on. And why do you think that is the case? Like, why is academia especially only doing fundamental research for our problems?
Why is academia doing fundamental, or why is academia uniquely equipped to do research?
Yeah, because I think in other domains we are seeing the industry is also doing fundamental research.
Yes, yeah. I guess I can only really speak to my individual interactions with some of these companies, and that they are moving so fast to corner market share that they are, it's about implement and user adoption. That is all that they, in my interactions with a lot of these companies, not on the record, I'm not saying any companies, but they are trying to corner the market right now, and that is front and center on all of their minds. And then, but they are, in their defense, really starting to think about how do we validate these things. So OpenAI and Anthropic did a bake-off on each other's models where they did an independent evaluation, and they've encouraged that. But they're not, it's just more of a, hey, we did this, that was cool, but they're really driven on cornering all of you. So.
Thanks.
We're going to switch to the next speaker, and then we can ask some questions of Ali and then both of them together, because I want to keep us somewhat close to on time. So thank you, Laura.
Yeah.
We're getting the slides together. So Laura spent a lot of time in government and certainly working with industry now. Ali is going to be giving the perspective of INCOSE, which is similar to what ASME is for systems engineering, although it's much, much, much more grounded in systems engineering practice. And so he'll bring the perspective from his role as the chair of the AI working group in INCOSE.
All right, good morning, everyone. And of course, they put me right after Sharma and Laura, so hopefully you'll bear with me. My name is Ali Raz. I'm an assistant professor of systems engineering at George Mason University, and I do wear multiple hats. I'm an assistant director for the C4I Center at Mason as well that does most of the national security research, and most of my research portfolio is systems engineering for national security applications. Another hat I wear is the chair for the AI working group for INCOSE. INCOSE is the International Council on Systems Engineering, and my sort of role today is to give you a little bit of information about INCOSE and what are the opportunities for AI and systems engineering and their intersection. So the way I've structured this talk is just a quick introduction to INCOSE and the INCOSE's AI working group, and then I'll lead into what, as a AI working group, the agenda we are putting forward for systems engineering and AI intersections. What are the challenges and how systems engineering and AI communities can come together to address those challenges. So anybody has heard about INCOSE here before? All right, oh, that's quite a few. That's good. So really, INCOSE is the International Council on Systems Engineering. It is one of the largest organizations for systems engineering network, about 26,500 members. in 71 countries. And it is, as Zoe mentioned, it is sort of like an ASME, but focused on systems engineering. One thing that I like to sort of bring forward is INCOSE was established in 1999 or around 2000 timeframe. ASME was in 1800s. So we don't have that much of a legacy as ASME or IEEE has, but we are very quickly building that up. Within INCOSE, there are multiple working groups that are focused on advancing the state of systems engineering from both academia, research, and practice. So there's a lot of corporate members that are part of INCOSE, and academia is also taking a increasingly larger footprint within INCOSE. And within INCOSE, about 5 years ago, they established a working group on systems on artificial intelligence systems. And I was one of the inaugural members of the AI working group, and now I'm the chair for the AI working group for the past 1 year. It is among one of the largest working groups in INCOSE. Typically, our working groups are about 50 to 300 people. AI working group has more than 1,200 members. So that's kind of gives you an idea of how important systems engineering community sees the artificial intelligence and what it will bring to us. So as part of that working group, I've been mostly part of that, and what we are doing is we're exploring the intersection between AI and systems engineering. Yesterday, Zoe mentioned about the SE for AI and AI for SE. SE for AI is how does the systems engineering community take their tools, techniques, practices, and help advance the AI. And AI for SE is how do we take AI tools and practices, techniques, large language models, reinforcement learning, and help them with the systems engineering techniques and methods and evaluations. So our working group is kind of like focused on advancing both of these activities and moving them forward. Some of the activities we've been very much involved in is among those 1,200 members, one of the things we continue to get is how do we learn more about AI? I think right now, we are in academia, mostly our students who are going through the degree program right now, I think they have a very good understanding of AI and machine learning. Anybody who got their degrees 10 years ago, chances are they did not take a AI machine learning course. I graduated from Purdue quite some time ago with my PhD. The first course that I took on neural networks was in 2012, and we had 7 students in that course. Right? So now I think it's probably you're on waitlisted for taking a course in neural networks. Anybody who got their degrees in 2015, maybe 2010, possibly did not get a formal introduction to AI. And that's one of the things that we are really trying to change within the systems engineering community is what is that foundational knowledge for AI and machine learning that the systems engineers need to know in order to do their day jobs going forward. Right? So they do not need to be perhaps the programmers or autoencoders, but they need to learn the basic principles for AI. So as part of that, we've been creating a lot of educational materials, we've been doing a lot of tutorials, and we've been writing a lot of articles on AI and systems engineering. And I think one of the reasons why that is important is, I'll mention this to you, is there's a lot of misinformation about AI as well. And AI, as it becomes very popular in our social circles, that is very common to see people like these. I don't want to say anything, but it was in Ottawa. It was an INCOSE conference in Ottawa, and I was about to go give a talk on AI. And I saw this gentleman standing right outside a pub, holding a sign saying, "Talk to me about AI, what AI is really all about." And I was like, yeah, I'm all about different perspectives, so I should probably at least spend some time there. So I went very politely, introduced myself, and I said, okay, what are your thoughts on AI? And the moment he said, it is the Satan's plans for the third world order, I was like, all right, thank you, I'm getting a little late. So I think that there's the reason, there's a need to promote AI education in communities that are not just going through college right now. Some of the other things we worked on is we created a special issue in Systems Engineering Journal on AI. And I think that's one of the first academically rigorous sort of body of literature that is going to explore the intersection between AI and systems engineering. So we have, unfortunately, the call for papers is now expired. We are going through our first revisions, and hopefully the first publications are going to come on soon. But I think that's probably one of the first INCOSE steps in creating a peer-reviewed body of knowledge for AI and systems engineering intersection. So hopefully, I think you all will take a look at that and and help us advance this forward as well. Because one of the biggest challenge, as in guest associate editor for this special issue, was finding reviewers on who could intelligently review both systems engineering and AI contributions. And I think I'm glad I'm here because you all provided me with a list of attendees for this event. So now I have a good, representative set of people that I could reach out to for these reviews. All right, so with that, I'm going to shift the focus a little bit on what is the systems perspective of AI and why that is needed, why it is different than training the deep neural networks or building machine learning algorithms. So beginning with the systems perspective, AI or machine learning algorithms, we would typically see them as a component of an otherwise complex or large system. What's different about these AI or machine learning algorithms is for the most of the time they're being deep neural networks, they're trained with these deep data sets, 80-20 splits for training validation, reward functions based on reinforcement learning, loss functions, what have you, and in the end it becomes a black box model. So it is a black box component of a large system. Now what that is a problem is because with SE perspectives, components within complex systems have interfaces to other components, and they interact with other components to create the system behavior. Oftentimes, that leads to an emergent behavior. I think one of the gentlemen yesterday gave a really nice example of a Boeing 737 MAX failures. Right? You might have heard about those, that they was trying to generate the angle of attack with a new algorithm. The sensor was reading the current location, and then there was a design decisions that were made that led to an emergent behavior of a failure. Now that's Boeing 737 is an example of a complex system. It does not have any deep neural networks because FAA has specifically said anything that touches a neural network does not come near an aircraft, right? So it is a components that we understand really well, the sensors we understand really well, the algorithms we understand really well, and still we have a challenge. But when we go towards black box models, then these are data-driven, they don't have well-established requirements, and we don't have controllability or observability of these states. And then they become part of a complex system that creates a problem. And that's the problem that we as a systems engineering community would need to address. So what are then some of the needs for these systems engineering for AI and ML? The reason there is that deep neural networks remain the most common form or the sexy form of implementation machine learning algorithms. When you talk to the computer scientists, it's all about benchmarks that we heard yesterday. It's about creating a new algorithm with a 1% or a 2% more efficiency, right? But in the end, those deep neural networks are black boxes. Their failure modes are not understood. There's a very limited characterization of their performance, and how they interact and interface with other components of a complex system, those are often not heard. So from an SE perspective, what is the variation of input sensitivities that would come from other components as an input to the deep neural network? How does that work? How does the uncertainties from an operational environment or the other components, how would that work? Those questions are rarely addressed. And that's the thing that, that we need to address as a systems engineering community on how do we transition these deep neural networks into practical system. Because a lot of times we're looking at a very rosy picture of AI, and we are forgetting a lot of times that AI, the A word is artificial, and a lot of times AI is only artificially intelligent. And there's a lot of case studies for that. This one picture that I'm showing, it's a little bit blurry, but I think it was like a cruise car that ran into a San Francisco city bus, right into it. And again, it was being trained on large language models. It was an image perception algorithm that was, recognizing that there is a bus. And how could that happen, that you go towards a physical test environment? This is not in simulation. This is not in a lab environment. This is not in a control environment. This is on a city street in San Francisco. And the cruise car ran directly into the bus. The reason was that the city of San Francisco decided to change the color on the back of their buses. Right? What we're seeing from these large language, these image recognition models is the benchmarks are at 95%. The best of the best algorithms, they perform at 97%. And they've been saying, oh, this is huge improvement. From a safety critical system, the requirements are 10 to the minus 9. That is 99.9999999%. So how do we bridge that gap from 97% to 97.99999%. AI community is not thinking about that, and then I think that's where we, as systems engineers, would need to come into play. And then, the examples are a lot. ChatGPT hallucinating court cases, Air Canada paying for the damage for the chatbot lies. Of course, from fintechs and from other companies, we are seeing a lot of value proposition from AI, and that is great. But the failures are also there, and they're rarely talked about. And the newest thing on the block, the foundation models, right? So foundation models are great. They're very powerful. They provide a lot of, let's say, step forward in our society, but they're also deeply flawed. This paper that came out about 3 months ago or 4 months ago in ICML conference from MIT, where they trained foundational models on planetary orbital motions, right? And they were very confident that the foundation model has learned almost everything that there is to teach a foundational model. And then they changed the mass of the planets a little bit. And it continuously failed to apply any Newtonian mechanics to those models, right? So even though all that data, it's really good at predicting the pattern that it has learned, as soon as you make a slight deviation, the responses are not there. So as a result of that, the AI community actually came up with what is called these unsolved problems in machine learning safety. And then they identify these 4 problems. One is called robustness, which is to create models that remain resilient to unusual situations or perhaps black swan events. Monitoring, detecting malicious use or detecting unintended consequences from these models. The other 4 are alignment, building models that conform to hard to specify human values, and systemic safety. So building models, AI machine learning models that can address risks such as cybersecurity or unintended environmental or operational considerations. So as I was going through these lists, and there's a paper from Berkeley and Google, the authors are from there. I was looking through this, I was like, perhaps systems engineering has a role to help address these unsolved problems in machine learning. And why that is the case is because I think that's some of the things that we have been doing for complex systems for quite some time, is addressing these types of problems. I'm not going to talk about the V model. I think Laura mentioned some of that in her slides as well. This is taken from Ollie DeVick's at MIT's course on fundamentals on systems engineering. So one of the things that fundamentally is taught in systems engineering is a V model that helps you take an idea or a concept from an idea and a concept all the way to a realizable product. And I could map those 4 challenges for unsolved machine learning problems directly to activities in these V models. So alignment, SE principles for alignment, that's one of the first things we would do is align a complex system towards the stakeholder needs or the stakeholder values. And there are tools, techniques, and principles within systems engineering community to help address those. Monitoring, that's again something we do is monitor the interactions or the interfaces of the different components of a system. And then there are tools, functional, physical, architectural analysis techniques that helps you expose those. I think one of the things we really emphasize on is systemic safety. So, and in systems engineering principles for systemic safety, that is detecting unintended consequences would be the probabilistic hazard analysis, failure modes analysis. There are all these techniques that are being done for complex systems, but they haven't been applied towards the AI yet. And the last thing we heard about robustness that Laura talked about, doing the test and evaluation before we launch a capability. But I think at the same time, I would say that I would be naive to say that systems engineering has all the solution. It may has the foundation, but I think there's a lot of research that needs to be done. If I say that take the V model that has been taught in fundamentals of systems engineering and we are ready for AI deployment, probably not. There's a lot of research that is being done on that side. There's different variations of those process models, of different tools and techniques are being researched in the SE community, and we need to bring it over to the AI community as well. Some formal methods, system safety, reliability analysis, those needs to be part of the AI development techniques. And then some of the techniques that are coming in AI community, for example, explainable AI or an ability to do counterfactual testing or reasoning, that needs to be then incorporated into an SE side of things. So just to keep on time, I'm going to give you a very quick example of some of the work that my research group has been focused on. That's, again, in the test and evaluation of the AI and how the systems perspective exposes some of the things that are often missed in the AI community side. So this is a project we did with Sandia National Labs, with Purdue University and George Mason. And then the idea was to explore reinforcement learning algorithm to provide a guidance commands to a very high-speed aerospace vehicle. So one of the first things you would ask is, okay, why not do the traditional control? Why not do optimal control? Because at high speeds, it's a very longer solution time to compute a maneuver. And human intervention is pretty much, very difficult at this point. So, okay, can AI help us with that? So the idea was that you have a vehicle model that is going through a certain space, that it's going to a target to land at some place, right? Can we use AI to guide this very complex dynamical system? I said, okay, let's try with reinforcement learning. We're going to start, and we're going to give it a flight control problem. It will start at a certain altitude, and it needs to descend to a certain altitude, and the controller would be a deep neural network that will be providing the angle of attack command. So basically pitch up, pitch down, and land the vehicle very nicely. So what you're seeing here is an angle of attack commands that are issued by a reinforcement learning agent. So I think the power here is that the reinforcement learning agent was able to learn the vehicle dynamics model, right, and provide control and guidance commands while meeting all the safety constraints, all the structural constraints to guide the vehicle. It took a lot of training and all of those things, but we were able to show that, okay, starting from a clean slate, the reinforcement learning agent can guide these aerospace vehicles. But then comes the systems engineering questions on, okay, I'm starting at a certain altitude, I'm going to a certain altitude. How about the altitude variations? Can it work on different altitudes? I talked to my computer science student. Yes, I have trained it on a initially randomly sampled space around the initial conditions. I was like, okay, perfect. And then how about, why is there a command at like 20 second of time or 25 second? Why not earlier? Why not later? How do I know? How do I know what is going on? I mean, once the cool infatuation phase is over and you start asking these questions, then it becomes a problem. I said, all right, let's do a Latin hypercube design of experiments and around these initial conditions and see how this reinforcement learning agent works and where does it fail. And it turns out it only works within the 5% of variation in the initial condition space. So then again, now you understand not even the performance, but the failure modes of that as well. And then we looked at different explainability techniques and looking at how the inputs to these deep neural networks, the initial conditions, the altitude, the velocity, the flight path angle, are impacting the controller design that it has learned. And what we saw was with these shapely additive explanation values is that altitude has the most impact as long as the velocity is not too high. If the velocity is too high, then it will try to descend. But that's sort of like a knowledge that I could take back to an aerospace engineer now. And I say, all right, this is how my deep neural network was working. Is that how you would design a controller for your vehicle as well? Because if you can expose that level of knowledge, then you can start to gain some trust and validation in the AI systems. So what I would say is, from a systems engineering perspective, taking these algorithms to practical implementation, these three disciplines, the systems engineering, because all complex systems are built from those principles, modeling and simulation, and AI with assurance, they sort of like need to come together and provide us a window of opportunity of how we are going to design these next generation of complex systems that adhere to systems engineering principles that are analyzed through modeling and simulation, and then they incorporate AI and machine learning algorithms. And that's not only me or Nkosi saying that. I don't know if you all looked at this report that came 2 weeks ago, September 30th of this year from National Academy of Engineering on machine learning for safety critical systems. I'm just keeping the takeaways directly from this report. And one of the things they keep on focusing is that the research and development communities for systems, complex systems, and machine learning, they have different cultures and they speak different languages. That needs to be brought together. And one of the key things that I would like to highlight is safely integrating these machine learning components into complex systems of the future. We need a new engineering discipline that would be at the intersection of machine learning and systems engineering. It's not my words, I'm directly quoting from this report. And the reason I wanted to highlight this is I think perhaps this is the community that will help create that new engineering discipline on how the intersection of these three fields with systems, design, and AI are going to come together to help us really take these AI ML algorithms into practical systems. So I think that's my sort of like last slide here. I would say please join the AI working group if you are members of INCOSE. Please join the AI working group. If not, become the member of INCOSE and then join the AI working group. And then that's one of the really the passionate area that me and our working group is really active in so advancing the state of systems engineering and AI together. So that's all from my side. I'm happy to take any questions, and if there is any follow-ups, please feel free to reach out to me. I'll be very happy to engage on these topics. Thank you.
We'll call Laura back as well. So I know there were some questions that I cut off before, so we can also start with those.
So I think this is a...
Laura, if you want to come up, maybe we can take questions together.
So this is a general question for all the systems engineers in the room. So many of these AI systems are developed with some objective in mind. But when you start thinking about it from a systems perspective, it's more depending on what the application is, depending on what are the other subsystems that surround and what are the interactions between those, the requirements may be different. So how should an AI model or a neural network model developer think about the possible usage of that model in different contexts to account for the kind of things that you discussed today?
All right, I'll go. And I think it's sort of the way, if you look at, as I was mentioning earlier, I think there is a lot of emphasis on benchmarks or looking at Hugging Face data sets to build these models, right? A lot of times, their outside considerations are not taken into account. There was just one example, I didn't code it in my artificial intelligence failures, was one of the vehicle accidents that happened. And what happened was there was a regular car and a self-driving car, all sort of together. And there was a pedestrian who's crossing the road, right? And they both see it, but the driver of the regular car, that's a human, makes an error and hits the passenger. Not the passenger, the pedestrian. The pedestrian unfortunately falls. The AI car has stopped at that point. As part of that accident, pedestrian falls and is on the ground. AI sees, oh, my scene is clear, and runs it over. And it drags the pedestrian almost like, certain feet until it detects a change in its driving condition. It's like, oh no, there's something's not right. So things like that, on a contextual reasoning side, that if you are designing, testing a system, are you taking into account those types of considerations? Before even you go into physical testing. I mean, these types of things could be tested in a simulated environment, right? But I think what we're seeing from accelerated deployment is that those are often ignored. And I think that's one of the things that systems, community systems thinking could help in building those models. So I don't know if I answered your questions or.
I have something to add.
Yeah.
Since you gave me some time to think,
Sure.
so I kind of want to echo. So I think that's a really hard question to answer, and I think it goes to exactly the point that you were making in terms of we need to bring systems engineers with machine learning together to start to tackle those questions. And I want to kind of go back to how important data is to understanding the performance of a model and thinking about kind of a general model versus a very specific model. And so I think that conversation needs, are we trying to come up with a computer vision to solve all computer vision problems? Or do we have a very specific thing we're looking for in the universe? And we don't care if it's bad at everything else, as long as it finds that specific thing and it doesn't incorrectly find other things as that specific thing. And so having those conversations about what the right modeling approach is always comes back to the intended use. And so I think that's where systems engineers can really bring a lot to the conversation, because right now, as you highlighted, it's all about benchmarks and getting from 97 to 98, but I might not actually care about 97 to 98 if, I go to 0. So I think having that conversation up front is important, and coming back to the data. And do I design a model that can be easily retrained, detect when I'm out of scope, or do I design a very niche model?
I want to add one more thing, because you opened it up to all systems engineering, because I hope some of this can, all the systems engineers into the room.
That is good.
But so I think one of the big perspective challenges that people who come from a computer science background and people who come from a systems engineering background, and I'm not going to impose what I think comes from a design background, but systems engineers start from concepts of operations, and the notion of operating envelope is really core to how we think about the world. And what that means is that we don't design systems to do everything, because we know we can't control outcomes for everything. Whereas the ethos right now with AI is general purpose technology. I can't possibly bound my operating conditions. And I think that's where the tension really needs to be, because you can't really test things and you can't really write requirements if you haven't decided some very broad conditions of how it's going to be used. But unless we're willing to have that conversation, then I see there's a lot of problems of putting the two disciplines together. Dale, go ahead.
Thank you very much. I think I've learned so much this morning being a systems engineer, aspiring systems engineer. Allow me a few minutes here to, hallucinate or confabulate, as the case may be. Take this as the musings of someone who is just, kind of wondering. Central to systems engineering are two key tenets. One is requirement analysis, and Zoe kind of alluded to that just now. And the other one is functional analysis. When you look at what they have at Stanford, they have what they call social innovation. They are very big on social innovation. And central to social innovation is the idea of human-centered design. We in systems engineering, we talk about systems thinking, right? Now that we are sort of transitioning to a new world where this world is no longer about humans, but also about machines. Machines, in this case, loosely defined AI systems. To what extent do you see us changing how we define functional analysis, requirements, engineering? To what extent do we now begin not only to cater to humans in the loop, but also, more importantly, to the machines that are still evolving, by the way? And it's one thing if we already have in place a system that is static. But here we're talking about a system that is dynamic. The AI of 2022 December is not the AI of, this is October 2025. And who knows what we're going to have come January 2026. So the question here is, how do you plan for a moving target with humans in the loop, where this moving target is the changing machine in the loop? Thank you.
Design for evolvability.
No, that's a very good question. I mean, I think that's one of the challenges that we do need to solve, is that how do you build systems that are learning or changing, constantly.
So I will just say that I think human-centered design is all that much more important in this new paradigm that we're in, because we were already kind of failing. So I work in defense. Our defense systems are unusable for mere humans. So I might be a little biased. There's a lot of great design system out there. But I think we already, with non-evolving systems, we already had challenges in making sure that they were really designed so your average user could operate them. So I think that is much more important in the current paradigm. I want to call back to another thing that Sanjay said, that in our educational endeavors, that we need to be thinking about how to, he said teach, but help our students learn about how to work in this new environment where we have evolving systems. And so I think that is an important lens to put on the human-centered design as well. It's the AI and the robotics and all of that is there. How do we modify human-centered design for that? And design, so compressing the systems engineering V, test early, test often, learn a little, and keep incrementing that back into your design. I think static system, thinking in a way that we can always be updating our system and our workflow, which is harder said than done, but it needs to be how we change our thinking.
Just thinking about the failure modes of AI, I'm wondering how much of it do you think can be just fixed by more and more data as well as more and more benchmarks? Because if you look at what's happening with autonomous vehicles and robotics, I mean, they're investing huge amounts in synthetic data and collecting human data and like more data about extreme cases, which could be failure modes. So just like thinking of, is it a modeling problem or is it more of like we need more benchmarks to test edge cases and more data to learn from them?
I can.
So, go ahead.
Oh, you can go ahead.
All right. So I'm all about the right data as an experimental design person. So I think more and more data is why we have, I don't know if anyone's been out the Dulles corridor where all the data centers are outside of DC. It's getting to be a little insane, and they're digging pipes to actually connect DC to Maryland, where they're putting, because we ran out of power in Virginia. There's no more power for the data centers, so now they're putting them in Maryland and they're connecting them through high-speed fiber. So I think that we will see the limits of more and more data fairly soon. And then we're going to have to figure out what to do about all this data that we've collected, because it's expensive to continue to store it. And so I think thinking more about the right data to solve the problem is correct. And going back to sound systems engineering principles on how we design systems, like you don't just have to have one AI model, right? You can have lots of AI models in your system, and those models can be good at different things, and you can model average, and you can orchestrate them, and you can have redundancy, and that's not expensive. So I think that is where I think the real opportunity is going forward, is in better systems design, leveraging these AI capabilities.
And I would add to that, I would agree with that, with the better system design. But I would add to that I think it's not only a issue of data, which is, of course, like extremely important, and those data centers are extremely gloomy to look at when you're driving through those. But I think it's also an issue of understanding on how that data is being used by these AI and machine learning algorithms. I'm going to go real quick back to this report, which came like from NAE on machine learning for safety critical applications, and it reports a recent study on changing the image for machine learning algorithms. It's not at a human distinguishable level; it's just at the pixel level. So there was a school bus, and it is still a yellow school bus, but in order to model like a cyber attack, they changed 5 pixels within that school bus. To a human eye, it is completely indistinguishable. But for a machine learning algorithm, it goes from a school bus to an ostrich. Yeah, so that's coded in that paper. That's a journal paper that takes about it. So how does it go from 5 pixels, which are indistinguishable to a human eye? How did that leads to such a drastic change? It's just we don't have that understanding of what happened within that black box. So I think it's kind of like both, that better system design paired with a deeper understanding of how these models are working. I think would lead us to those futures. So.
But do you think just more data will ever get you to safety critical, the 99.99%?
I think that's the understanding piece that will come along with it, right? So, yeah.
And just to emphasize one thing that you guys said, benchmarks are really not popular in systems engineering. The goal is discovery, not optimization when we're early stage, and I think that is a difference in kind of how we formulate our problems in the two disciplines, and I think that's really important from a humility perspective of we keep seeing how bad we were at figuring out what we needed to measure. And so if we can take a moment to actually discover what we should measure before we start measuring and optimizing to it, that's hopefully going to avoid some challenges.
Thank you.
Yeah, from my perspective, I don't think the more data is, more data of course it will be helpful, but we really need to think about what kind of data we really need. For autonomous driving, right? If you are driving in the normal case, okay, those more data, they are normal. Actually, they are not very useful, but really the autonomous driving we need to deal with the edge case, right? There is something bad happen, as you mentioned, like for example, the people fall down, or maybe the kid is running in the parking lot, and those edge case, the outlier data is really what we need. Mm-hmm. Not just and also you are talking about the better design of the system. I think those future machine learning model, they really need to have some common sense. They need to think, they need to reasoning, not just trying to look, right?
Yeah.
Thank you. Well, we've blown through our time, so let's thank the speakers one more time.